Dear colleagues, it's my pleasure to welcome you at the Minisymposium on heat and energy transfer in discrete systems. And so I would like to pass the word to Professor Oleg Gendelman from Technion University. So he will be giving the keynote lecture.
So I would like to give an overview of some works of a very fascinating topic about front propagation or transition fronts in bistable non-degenerate systems. These works were performed over the last couple of years with my PhD student, Shiroky. Now, what this story is about? There are many systems in which transitions of all kinds can be described in terms of propagation of fronts in non-degenerate bistable systems. So here you see, I'll try to use laser pointer, yes. Here you see the chain with on-site potential, which has two wells, yes, and these two wells are of non-equal depth. So when the particle goes from metastable well to the stable one, the energy is released, and this energy release is what supports the front propagation. So there are many physical systems in which such models are used. For instance, dislocations, magnetic avalanches, yes, crack growths, yes, even in some biological systems, yes, calcification, cardiac myocytes. Yes, now just two brief examples. For instance, in acetate, it is possible to have two orientations of magnetic momentum, and it is possible to see the magnetic avalanches. So the waves of transition from one orientation to the other. Yeah, I'll bring here a reference, yes. So when you put appropriate sensors and look at the orientation of magnetic momentum, you can observe the waves of switching wave transformation with some oscillations at the tail. Yes, okay, these are dissipated, of course, but this is what you see. Of course, when this front propagates, the energy is released, and you're going to see some oscillatory tail after the front. The other example may be propagation, but now is my favorite one. It is collapse of carbon nanotubes. So this is carbon nanotube, and here you see what is referred to as collapse. When you have circular configuration and somehow press the tube, then you have this wave of collapse. Why it happens? Because if you look at carbon nanotube, there are two equilibrium configurations: circular, which has minimum of elastic energy, yes, and collapsed, that elastic energy is higher, but there is a big gain in terms of van der Waals interaction. So for a large enough nanotube, the gain is large enough, and collapsed configurations is stable. So one can observe the transition, yes, and of course this transition is, in the simplest approximation, can be described by this model. So on previous slide, yes, this is some realization of nanogun, yes. So when you have particle inside the nanotube, it can be thrown out with the help of this collapse. Okay, now, so what I'm going to discuss is a sort of theory that we suggested for this phenomena. And also, it turns out that even in that simple system, when you have just a chain in this non-degenerate bistable potential, you can observe very different patterns of front propagation. So the origins of this activity, they date back to famous Frankel-Konturova model. Yes, in general, this Hamiltonian of this model is described by a nearest neighbor interaction in this case, and also the on-site potential. Main physical parameters of the potential are, as you see on this plot, yes. Q is the energy effect, yes. B is the height of the barrier, and then phi star is the coordinate of the barrier. So these three parameters are basic physics parameters that characterize the potential. Yes, there may be more, but still turns out that these are among the basic. But of course, there are many particular realizations of potentials can conform to these definitions. For instance, we plot here the fourth order polynomial, sixth order polynomial, and biparabolic approximations with the same basic parameters. So the question is really what parameters, what physical characteristics of the on-site potential are most important, and how they determine the particularities of the transition we observe. And what are these particularities? In these sort of models, we can see very different modalities of front propagation. I'll show you these pictures, yes? So for different chain models and for different on-site potentials, you can see very different patterns of the front propagation. I'll start from the left, yes? Here, actually, you see the front, but before the front, you see something else. So it is what we call non-traveling solutions. So the front propagation cannot be described as traveling wave. Here, we have very, here already, we have traveling wave. Yes, the front propagates with subsonic velocity. Yes, and if our chain would be infinite, it will be described as traveling wave. But the most interesting, perhaps, is the right simulation, because here we see something very peculiar. The front propagates extremely rapidly. It is a subsonic regime and a supersonic regime, and it can go to, say, 2-3 sonic velocities in the chain. Yes, and oscillatory tail is formed, but you can see visually that it has a very low frequency. So it has very long wavelengths. So these distinctions are not unknown in literature. For instance, in a well-known book of Professor Tuskinovsky, such slower fronts are characterized as kinks and faster fronts as shocks. But what is underlying mathematics is not completely clear. So let us take a closer look. First of all, we'll start with traveling kings, the intermediate case, when the front propagates as a well-defined front without all these precursors, but with subsonic velocity. So the first work in this field was by Atkinson Cabrera in 1965, where they considered harmonic chain in piecewise parabolic bistable potential. In this case, it turns out it's possible to solve the problem exactly and to find the velocity. But what we observed, that quite expectedly, as we modify the on-site potential, we see effect on the front propagation. So here on this plot, you see that for 3 different potentials, we get different, although similar but different dependencies on the velocity, on the parameter of potential. And of course, these 3 potentials have the same basic parameters. As you see, for biparabolic potential, these parameters are everything that is required to find the King velocity. So for Kings, yes, for subsonic Kings, the velocity strongly depends on the on general characteristics on the on-site potential. However, what happens for supersonic shock waves? We see something very different when we see them, when the nearest neighbor potential is nonlinear. We'll see for the examples, but say Fermi-Pasta-Ulam chain or things like that. If we take into account the linearity, the patterns of front propagation become very different. So first of all, the front becomes very narrow. Actually, in this region, we see hardly 2 particles. So it is extremely narrow. It's extremely rapid, far supersonic velocities. And the waves in oscillatory tail is, as you see, is very well defined. It is very nice. And it consists of very long waves. So actually, we use here somewhat simplified analytic model. Simplification is based on the mere fact that a huge amount of energy is concentrated in the front, and is so huge that it is possible to neglect the on-site potential in the front region. Yes, then it is possible actually to reduce the dynamics in the front region to the system with 1 degree of freedom, yes, provided that the particle starts from some initial coordinate, 0 actually, from the metastable state, and after the front passage, it goes to the other state, which is defined by the potential we immediately see what. After passage of the front, if particle starts here, for different potentials, it jumps to different points. The points characterized by the same energy, because this reduced model in the vicinity of the front is conservative. Now, out of this model, we can compute the velocity of the front, yes, and then these are some results. So quite surprisingly, we see the universality. It means that in very different potentials, in very different side potentials, these shock waves behave in the same way. So you see here the quality of the collapse, yes, for very different potentials. And it turns out that actually the front velocity depends on the single parameter of the on-site potential, this delta, which will be immediately defined in a more clear way. So we see that also for regular Fermi-Pasta-Ulam with alpha and beta terms. So it is completely describable and in very nice agreement with numerics. So also we asked ourselves what happens with Lennard-Jones potential, and the same. If we use correct universal parameter, then for all on-site potentials, the results collapse on the same curve. And what is this result? Here it is. So again, this is this delta, the distance between the point of equilibrium to the point of the same energy on this rising branch of the on-site potential. And here are simulations for quartic nearest neighbor coupling, yes, and for very different on-site potentials. Now I switch the simulations, and you can clearly see that the velocity is the same, yes, despite the fact that, of course, because of strong linearity on linear coupling, we have different oscillatory tails, but the velocity is the same. So indeed, it is possible to find a single parameter that characterizes the on-site potential that gives a complete prediction of the velocity of the shock waves. With one observation provided that the energy difference is sufficient, that you get enough energy to continue the process. So we have here a sort of nice universality, which was quite unexpected. So it is characteristic of the shock waves, but not on the subsonic kings. So shock waves, supersonic waves are in this sort of systems are easier for description. Okay, now I see that my time starts running low. What with the damping? Yes, if we add the damping to the system? No problems. The damping, of course, affects the oscillatory tail. It now vanishes, yes. But in the vicinity of the front, it can be considered as small perturbation, and still the same parameter of the on-site potential defines the front velocity. Here you see simulation results for even not necessarily small damping, yes. Now we would like to take a look on the third modality of third situation, these non-traveling solutions, or what we call them oscillating kings. What happens? These kings appear as the result of the loss of stability of traveling kings. And it is possible to formulate more or less standard stability problem for the map that describes the translation of the king by one element of the lattice. Yes. So this is the example of this instability. You see this oscillatory tail that goes before, it's not tail, it's front, oscillatory front that goes before the king itself. Yes. And the king, pure king, can be seen as a periodic solution of some harmonic, of some discrete map. So the bifurcations or loss of stability can be described in terms of regular bifurcations of the stationary states of the maps. So I'll not go into details. It is possible to, for biparabolic case, it's possible to do that analytically, yes, to derive the stability conditions. And now what we observe is a sort of normal Hopf bifurcation. So before the bifurcation, we see just traveling king. And after the bifurcation, we see this oscillatory tail, this oscillatory behavior. Now, for more complicated models, when we take into account the spinodal region, it is possible also to perform all these calculations. And what we get very interesting pictures that these traveling kings, they lose stability by these well-known Feigenbaum sequences. Yes, and we can even observe chaotic propagation of the kings. So one additional observation was that these losses of stability are related to internal resonances between the frequency of oscillatory tail and the frequency of king propagation. I mean, frequency propagation is 2 pi over time of travel between side to side. For smooth on-site potential, we used force power polynomials. The bifurcation diagrams are more complicated. We also see some periodic solutions, but we see also there was a nice observation, coexistence of stable Kings. So for the same set of parameters, we can observe propagation of Kings with two different velocities dependent on initial conditions. So there are many works, many attempts to relate the King propagation in such systems to some natural friction, natural damping caused by the lattice. So the fact that we can observe different velocities means that it is not possible to derive this unique function for this dynamical friction. There is no such a thing. Okay, I think that we have also some results for the systems with self-excitation, but I'll prefer to skip them. Yes, unfortunately, there are many. Yes, and to close this, we have, even in the simple system of the chain on site foundation, yes, we can observe very different patterns of the phone propagation, yes. So we found very interesting universal behavior for very rapid shock waves, yes. And as for the Kings, yes, we can relate them to stationary points of discrete maps, and we find all family of classical generic bifurcations. I think that I'll stop here because I see that my time is about over. Thank you.
Yes, thank you very much, Professor Gendelman. Very interesting lecture. So now we have a little bit of time for questions. So any questions, please? Okay, so let me ask the question. So how would the finite temperature of the system influence this propagation of shock waves and all those front waves and so on?
Okay, we have analyzed this numerically for okay, I'll come back to these three regimes. Finite temperature, first of all, it has effect only if it is comparable with the energetic effect of this transition. Yes. So otherwise, it has very small effect. But what we observed, yes, for finite temperature, that in this model where we see these slow Kings, so you can get pinning, you can get actually you can get excitation in other places, and even you can have multiple Kings, because imagine that you just excite the chain. So it is non-zero probability that at some spot you will get excitation just in the middle. So it is, if the temperature is not too high, it is difficult to see this, but for finite temperature, the transition is very different. Actually, the system explodes everywhere.
Actually, maybe I will follow this question that in real systems, the energy of temperature oscillations can be even much higher than the energy of the shock wave. What would you expect in this case?
We didn't try that. We didn't try that. Temperature, so what you call energy of shock wave.
Well, this is not well. We can compare by the way if the shock wave travels and if it can heat material to a high temperature. Well, it means that the energy is comparable with the energy of.
You see, interestingly, no. So maybe I understand your question, and yes, if we if you now look here, so when we speak about shockwave, so it has very interesting properties. Energy in the oscillatory tail is of course equal to Q. I mean energy concentration. It is quite obvious from the equilibrium conditions. But the energy concentrated of the formation concentrated in the shock wave on the front can be by 2 orders of magnitude higher. So, so at least in this model, we see extreme energy concentration on the front of the shock wave. And that is why, by the way, it has so universal properties, because we can neglect many things there.
It's maybe
but in the tail, yes, in the tail, it is just the energy effect. It is what you get out.
Okay, so we have to proceed because we are already running out of time a little bit.
Yes.
So thank you very much, Professor Gendelman, once again for the very interesting lecture.